about heat, and the question we're going to discuss is the same snowboarding question, where a snowboarder is traveling on a 3.2 kilogram snowboard that is made out of steel, and when he stops, the board has a temperature of 15 degrees. And what we're supposed to do is to calculate the energy that is released when the snowboard is cooled to 5 degrees. And here's the equation we're going to use, Q equals mc delta T. By using this equation, we can calculate the amount of heat energy that is released, the amount of heat energy that is needed when the snowboard is cooling down. So we're going to plug in what we already know. The mass of the snowboard is 3.2 kilograms. And the specific heat capacity, C, of the snowboard, which is made of steel, is 450 or 4.5 times 10 to the power of 2. And the change in temperature we also know. The change in temperature is from 15 degrees to 5 degrees, where 15 is the initial temperature and 5 is the final temperature. And we're going to plug these numbers we got into the equation. So first of all, plug in the mass, 3.2 times 4.5 times 10 to the power of 2 times changing temperature. And changing temperature is defined by the final temperature minus the initial temperature. And when we multiply the numbers together, here's what we got. 3.5 times 4.5 times 10 to the power of 2 equals 1575, and the T final minus T initial, which is 5 degree minus 15 degree, equals to negative 10. And we multiply the two numbers together, and the final answer will be negative 15,750 joules. So therefore, the snowboard release 15,750 joules to be cooled to 5 degrees from 15 degrees. For part B, the snowboarder has left his snowboard on a pile of ice that's weighing 60 kilograms, and the ice temperature is negative 10 degrees. And what we're supposed to find is the final temperature when the two objects are combined. And so for this question, the first thing we're given is the mass of the snowboard, which is 3.5 kilograms, and the initial temperature of the snowboard, which is 5 degrees. The second thing we're given is the mass of the ice, which is 60 kilograms, and the mass of the temperature, the initial temperature of the ice, which is negative 10 degrees. And now we're going to use the principle of thermal exchange to figure out the answer of our question. The principle of thermal exchange states that when thermal energy is transferred from a warmer object to a colder object, the amount of thermal energy released by the warmer object is equal to the amount of thermal energy observed by the colder object. This means that the warmer object transfers thermal energy to colder object until both objects have the same temperature. So the equation of the principle of thermal exchange would be this: Q release plus Q observe equals 0. In this case, the snowboard is the releasing source because it has a higher temperature. So M1C1 times TF minus 5 plus M2C2 times TF minus negative 10 degrees equals 0. And this one is the Q release, this one's the Q absorb. And now we plug the numbers in. So for M1, it's 3.5, and C1 is 450, the specific heat capacity, and TF we don't know, minus 5 plus M2 is 60. The specific heat capacity of ice is 2100. That can also be found in the textbook. And TF we do not know, and because it's a double minus here, number is added. So we add 10. And then the final answer is still 0. And we multiply what we already know. 3.5 times 3.5 times 450 equals 575. And we distribute that to the components in the bracket. So this amount of TF minus 8 plus 2600 T final, and and we collect like terms and put the variables on one side and the numbers on the other. And we add these numbers together. And then we isolate for TF. And the final answer is negative 8.87 degrees. And therefore, the final temperature of the ice and the snowboard is negative 8.87 degrees. And this is calculated by the principle of thermal exchange, where Q release plus Q absorb equals 0.